Hey class, and welcome to your pre-lab #1 video. Keep in mind, on all of these pre-labs, you need to go in and download the lab, answer the questions on your own initially, and then watch this video. So if you've not answered all of the questions and attempted them, then you cannot be watching this yet. You need to do that first and then come here. Again, even if you're not sure, I want you to get in the habit of guessing, making your best educated guess that you can. All right. So again, I'm going to share my screen here. But you should have downloaded the lab and you should have looked at the different questions as you see here. Again, questions 1, 2, 3, 4, and 5. There's a total of 5 on this pre-lab. And you should have been working on your own attempts. So you should have something either handwritten on a piece of paper or typed out that looks like this, with a column with all of your guesses on one side and then a bunch of blanks on the other side that we're going to fill in together as you watch this video. So let's take it from the top. Question number 1, as we saw, asks us, what are the steps of the scientific process? Now, there's, again, various different ways that you can go about answering this. Sometimes you'll see it as 4, 5, or even 6 different steps. I just wanted to boil it down into 4 basic steps. So the first, as you probably know, is to make an observation or ask some sort of question about the physical world around us. Something like, as we're going to do today, at what rate do objects accelerate towards the Earth when dropped? Or you might ask something like, do different objects accelerate at the same rate? Those kinds of questions. Again, it's the starting place of the scientific process is making an observation and asking a question. Now, the next step, sometimes people will break this into 2 separate steps, but I like to say the second step is to make a hypothesis based upon background research. So sometimes you'll have the research or background knowledge be separate. In this case, I put them together. So what this means is on every lab, you need to be thinking about what is your hypothesis. And in fact, many times our pre-labs are designed to walk you through the process of forming a hypothesis based on the things we've learned in class. So most of the times your background research will really be watching the lecture videos and getting a grasp of the physics we're dealing with. So you want to make an observation, ask a question, make a hypothesis based on research, and then you conduct a test to test that hypothesis. So you test your hypothesis, and then you draw conclusions based upon that hypothesis. Now, that's the overall scientific process, but again, that's what you're going to be doing time and time again throughout this course, and it's really something that all scientists do time and time again in their daily tasks, and I think many of us do it just in our day-to-day life. For example, my wife makes fun of me for the way I load the dishwasher. I load it like a scientist. I am constantly, what's the best, most efficient way, both in terms of time and space efficiency to get everything in the dishwasher for loading it. And I'm always doing different little tests to try to hypothesize, oh, maybe putting the bowls on top will be better than on the bottom and so on. And then I draw conclusions based on how much I can actually get in the dishwasher. Now, that's not the best example, but it is a good one. Part of my test is also whether or not they actually get cleaned, which is important. So pre-lab question 1. Now, if you had this already, if your guess was these 4 things, then you could have just typed all correct and you don't need anything in the right column. But oftentimes some things will need to be corrected. So you'll add just the corrections. Or if you had like 1 and 2 and missed 3 and 4, you could again just leave 1 and 2 as being correct or whatever, and then done 3 and 4. But anyway, question number 2 asks us about the different types of air. Now, again, there's multiple correct answers here, different ways of really saying the same thing. Sometimes people have 3, 4, even 5 different forms of air. I just break it down into 3 general categories. The first category of air that I usually would encounter as a scientist is what we call random air. Now, this isn't an inevitable air. That's just, again, the nature of the limitations of our different devices. As you'll see in today's lab, using the same ruler or meter stick to measure a piece of paper, to the accuracy of that meter stick or tape measure could actually give you slightly varied results due to the limitations of the accuracy of the tool and you as the observer. So some amount of random error is normal, and it's about the limitations of our tools and about the nature of doing scientific experiments. If you ever have an experiment where every single answer is identical, I would be skeptical looking at your results of whether or not you did it well and measured to the accuracy of your tool. Because if you're just rounding and they all come out the same, well, there's probably more accuracy in the tool than that shows. So random error, normal, you want to try to minimize it, but it's always going to be there no matter what. The second is human error. As the name sort of implies, that's where you as the human make the mistake. and cause some sort of error to occur. And then the third is what we call systematic error. Now, systematic error is, again, a type of error that you, as the scientists, are going to want to try to minimize as much as possible. So you want to minimize the systematic error, which is, again, as the name implies, some error in your system, an error maybe with using a miscalibrated tool, or you have a design flaw in the way that you do your experiment. Like sometimes I've had students do a countdown, 3, 2, 1, release, and the person releasing is doing the countdown. And so it's like 3, 2, 1. And like as soon as they start of 1, they let go. And then the person down timing is like 3, 2, 1. They wait till they hear 1, think about 0, and then hit start. Every single trial, their time is going to be too short rather than accurate. And so that's an example of systematic error in the way the experiment is running. So again, you as the scientist need to think about how you can minimize both human error and systematic error when you do your experiments. All right, so now we're going to move on to pre-lab questions 3, 4, and 5. And for that, I'm actually going to use my my iPad as sort of a whiteboard here. So I'm going to share my iPad with you. All right, so here we have question 3. Again, I'm showing you what it could look like if you choose to do it using a handwritten version. Again, your attempt on one side and a correct answer on the other. Keep in mind, anytime I'm asking you for like a derivation or an equation or something, like we see here, I don't want you to just write just the equation, but rather I want you to show me the steps that lead to that equation. So that's what I'm going to show you here. What are some different ways to experimentally determine the acceleration due to gravity? Well, there's actually quite a few. You could make a pendulum and time how long it takes to swing back and forth. There's equations that you can use to derive an equation for gravity from a pendulum. But what we're going to do is use the information that we're just now learning about kinematics. So what I want you to do in this lab, as it explains, is I want you to stand somewhere up high here. Here's you standing, upstairs on a balcony or at your back deck or something. Here's the ground, and you're going to drop something like a tennis ball. And here's you being real happy because you're doing your physics lab. It's your favorite part of the week. So you're standing up here, you're going to drop the tennis ball, and you're going to time how long it takes to fall from a measured height. So again, if you measure this height and you measure the amount of time it takes, you can actually figure out the acceleration due to gravity. Let me show you how that works. Well, treating this like a physics problem, we have a picture that we started with here. Let's label our kinematic variables. So one of our kinematic variables is x initial, or in this case, since it's vertical, I'm just going to use y instead of x. So y initial is my initial position in the y direction, which I'll call h, that initial height we're starting with. So what that means is I'm calling this sort of my axes here, and I'm defining this as the 0 height. So again, this is something that we're going to measure. Okay. Then my initial velocity in the y direction, the initial velocity from which I'll drop it is going to be 0 meters per second. So you need to make sure you're just releasing it, not like throwing it down or something. Okay. Down here at the bottom, my final y position is 0 because we're measuring the time till it hits the ground. And my final velocity in the y direction is something I don't know. And I don't have an easy way to measure that. At least I doubt you do at home. The time it takes, I'll just use the letter T to represent, but again, that's something we're going to be measuring with a stopwatch, and you got to come up with a method to be as precise as possible for that T value, or else you're going to be off. And then the last thing is the acceleration, and the acceleration is g, but g in the downward direction. Keeping in mind, g represents the magnitude of gravity, so I'm putting negative g since it's downward. And it's this that we want to figure out an equation for. So one of our kinematic equations of motion is as follows. It says y final equals y initial plus v initial y times time plus 1/2 the acceleration in the y direction times time squared. So that's your kinematic equation of motion that we're going to be using. So again, to show me an equation in a pre-lab, I don't want just this or just what it comes out to, but the step-by-step process of how you get to the final result. So you start here, and let's plug in the values based on our scenario. So this is y final is 0. So 0 equals y initial is our measured height, plus v initial is 0. So 0 times anything is just 0, plus 1/2. Our acceleration is negative g times t squared. And now I'm going to algebraically solve for g. So since I have minus 1/2 gt squared, I'm going to move that to the other side of my equation, making it positive. So positive 1/2 gt squared equals h. I'm going to multiply by 2 and divide by t squared, and I get g equals 2h divided by t squared. And so this is the equation in today's lab that we can use to measure the acceleration due to gravity. So that's pre-lab question number 3 for you. Pre-lab question number 4 here, I'm actually not going to go into a lot of detail on in this video because it's really in all the lecture videos. But you can really kind of summarize it briefly in that velocity is the rate of change of position, right? It's displacement over time. Or if you're in calculus, right, then it's the derivative of position with respect to time. But it's really just the rate of change of the position with respect to time. And similarly, acceleration, meters per second or meters per second squared, is the rate of change of velocity with respect to time, or the derivative of velocity with respect to time. So that's pre-lab question number 4 for you. You can kind of write that out in your own words, and hopefully you had that correct already. And to practice that, pre-lab question 5 enables us to do that. So here we're asked to make 12 graphs. So if you don't have 12 graphs sketched already in your attempt, you need to pause the video and read the instructions more closely. It asks you to do position versus time, velocity versus time, and acceleration versus time, each of those for A, B, C, and D. So as you can see in my little example here, I have A, B, C, and D, and each of those has position, velocity, and acceleration graphs sketched. They're not beautiful, but they should work to get the point across. So let's start with this first one. We have an object that's moving in the positive direction with constant speed. So since speed is the magnitude of velocity, something moving in the positive direction with constant speed means there's a constant velocity. So in fact, maybe it's easier to start with the second graph. Let's just start with velocity, a positive constant velocity. So I'm going to have a flat positive curve that looks something like this. And what that means then for my position is that my position, since velocity is the rate of change of the position with respect to time, my position is going to have a constant positive slope. So it might look something like this. And then similarly, the acceleration is the rate of change of velocity. If you have a constant velocity, you have zero acceleration. So my acceleration is right here on the 0 line. Now moving on to the second one. Now we have an object moving in the negative direction with constant speed. So again, it's moving in the negative direction. It could look something like this. Although technically it doesn't tell us where we start. So this would also be accurate. It's moving in the negative direction with a constant speed or something like this. Any of these could be accurate, even different slopes and so on. So any of those would work, but I'm guessing most of us would have guessed something like this, which is totally fine. Now, sometimes I see people do something like this. That's going backwards in time, and that is not something that we've ever figured out how to do. So you cannot time travel. So make sure that you're going down, but in the positive time direction. So similarly, our velocity is constant, but since it's a negative slope or negative direction, we have a constant but negative velocity. So notice I'm below 0 there, and we still have no acceleration because, oh boy, howdy, I accidentally switched markers. We have no acceleration since there's no change in velocity still. So there's the first two. Now we're moving on to part C, which is an object moving in the positive direction, gaining speed at a constant rate. So this one's a little trickier. Now, sometimes people will start with position, but I actually like to start with either velocity or acceleration. In fact, maybe I'll start with acceleration. We're told that it's gaining speed at a constant rate. So that means it has a positive and constant acceleration. So right there, boom, positive and constant acceleration. What does that mean? Well, that means then that there's going to be a constant positive slope of our velocity graph. So we're going to have something that looks like this, a constant positive velocity graph so that it's gaining speed at a constant rate. So it's going up, getting faster and faster all the time with a constant slope. So it's a straight line. And what that means then is that the slope of our position graph is going to be constantly increasing. Since we're going faster and faster, this is where we're going to have like a parabolic curve, something that looks like this, because we're gaining speed and therefore covering more distance per unit time with each second that goes by. So that's what your part C should look like. And the very trickiest one is actually part D, because we have an object that's losing speed at a constant rate. However, we're told it's moving in the positive direction. Oh boy, so this one's tricky. Let's again do it the same way. Let's start with acceleration. So we have a constant and negative acceleration. That part's pretty straightforward since we're losing speed at a constant rate, and acceleration is the rate of change of velocity, and speed is just the magnitude of velocity, right? But now with the velocity graph, I even messed up my picture here. We're told here that we are losing speed at a constant rate, but we're moving in the positive direction. So that means we're going to have a positive velocity, but it's going in the downward direction at a constant rate. So it actually would look something like this. That would be a constantly changing velocity, losing speed at a constant rate. So it should look something like that. And in fact, actually, I should probably change my graph just slightly here and make it extend the whole time. But it should look something like that. There we go. Okay. And then what that means for our position as a function of time, it means since we have a positive velocity, we have a positive slope. So we're still moving up the entire time, but that slope is going to be decreasing. So we're going to look something like this is what our position graph should look like. So some people would wonder like, whoa, wait a second, like what would even do that or what might look like that? If I were just to take a ball, like I have my trusty little ball right here and toss it straight up, boom, done, did it for you right there. As it was moving up, it was losing speed at a constant rate, but going up the entire time. Eventually it reached zero velocity right at the peak before it started falling back down. But that on the way up would be exactly that graph that we saw in part D. And then once it reached the top, it would start coming down, and then it would look slightly differently. So that's your pre-lab. You should have all of these answers, your guesses and the correct answers. I want to see both of those. I don't want any erases or anything. I want to see what you guessed. I don't care if your guesses were wrong. I just want to see both columns with the correct answers in the column on the right. And you can upload either a PDF of that from an iPad, from the computer, or from a picture that you took. If you have any questions, let me know. Have a good day.